All right, welcome to the AdaptX podcast, where we have conversations with individuals who are building accessible businesses, advocating for inclusion, or excelling in adaptive sports. Our intention is never to speak on behalf of those with disabilities, but give them a platform to amplify their voice and share insights and information that can make your world more accessible. Today, we are joined by Tom Otis. He is a researcher, academic, and author. He is the chief scientific officer at Therapeutics and is a professor of neuroscience at the University College of London, where he also serves as the chief scientific officer at the Sainsbury Wellcome Center for Neural Circuits and Behavior. His background spans 30 plus years of experience in both academia and industry. Prior to his university position, he led a team of 45 scientists conducting early stage drug development in neurodevelopmental disorders and psychiatry at Roche Pharma R&D in Basel, Switzerland. I already forgot what you mentioned. Before Roche, he served as the Edith Agnes Plum Chair of the Department of Neurobiology at UCLA. Tom received his bachelor's and master's degrees in biological sciences and his PhD degree in neuroscience from Stanford University. His research is focused on cellular and circuit function of the cerebellum and hippocampus, motor systems function and motor learning, and preclinical models of epilepsies, spinocerebral ataxia, and amyotrophic lateral sclerosis, better known as ALS. Probably the most impressive and lengthy intro I've had so far, and I only butchered a few words, so I'll call that a win. Tom, thanks for joining us today.
No, it's my pleasure, Brandon.
All right, let's dive in. I'll do my best to keep up. So for our listeners who might not be familiar with SEA, so spinocerebellar ataxia, or ALS, can you maybe provide an overview of what they are, maybe any intersections or individualizations?
Yeah. So I'll start with spinocerebellar ataxia. These are diseases of uncoordination, and they're neurodegenerative. So parts of the nervous system, the neurons die, and this causes the symptoms. And these neurons are mainly in a structure called the cerebellum, which is critically important for coordination, coordinated eye movements, balance, and motor learning. So in sport, this is a part of the brain that's really important. And these diseases, the other thing that kind of sets spinocerebellar ataxias apart, see, even I can't say it, is that they are predominantly genetic. So there are genes that cause what we call a gain of negative function. Just means that the gene is doing something bad, and it's doing something bad that affects, in particular, these neurons in the cerebellum. And so hence the disease. In ALS is a disease of motor neurons. So it principally strikes the motor neurons in the spinal cord and in the brainstem. And these neurons, it's also degenerative. And so these neurons die, and people gradually become unable to move. So they become gradually paralyzed. In ALS, it's quite interesting and similar to some of the other major neurological disorders in that we know many genes now that can cause ALS. So about something like 15-20% of ALS cases are caused by known genes, single mutations. And then the remainder of ALS cases are complicated. They're unknown origin. They might be many genes that are kind of together failing to cause the disease.
The introduction of CRISPR allowed you to more accurately assess the genome. Has the nature of your research changed a lot since that was introduced?
It has, in the sense that it's a tool for not only potentially, maybe not quite yet, but potentially for transformative medicine to edit genes. That promise is there, and there are a lot of people working on this, a lot of companies as well. But it's a tool that's important for research. So it enables you really to go in and with precision rewrite a genome, either a part of a gene, and correct, for example, a mutation, or to remove a gene, or to alter it in a certain way. So in exploring these things, the biology of these things, it's a huge and important tool. Similar to many people remember the PCR technique, which heralded an explosion in forensics and study of the human genome, where you could really amplify small parts of DNA, also human origins, right? Fossils and Neanderthals and all that. PCR about 25 years ago, I would put CRISPR as a similar transformative advance.
What influenced you to kind of delve into like the field of neurodegenerative diseases? Was there any personal experiences that influenced that career path, or?
When I was making the kind of the real early career path decisions when I was studying at university, neuroscience was fascinating. So I was first hooked on neuroscience, and actually that happened, or key events when I was an undergraduate. I actually was really captivated by Jacques Cousteau, and so I wanted to be a marine biologist. And Stanford has a marine station in a beautiful part of the California coast in Monterey, and I studied there. I went and studied there, and part of the lab work was with sea slugs and squid and things like that. And these were, at the time, this was in the mid 80s, these were classic preparations where you could study neurons and neural function. And so I kind of became fascinated with how neurons can work and signal, and they form the basis of not only movement and all action that we take, but all the cognitive stuff and memory and all of that. So then I went to graduate school, and I learned, because it was a lot interspersed with the medical students, I learned a lot about diseases in the nervous system, and they're, of course, they're devastating, and it's really a mystery even still. Many of these diseases, we don't have a good understanding of what's gone wrong. Like most people, I've had relatives who've had certainly age-related dementia and other sort of insults to the nervous system.
Yeah. What are the biggest challenges? I know there's a lot of unknowns, and this might be too vague of a question, but what are the biggest challenges in kind of identifying some of the epidemiology and the genetic causes of these conditions?
Yeah. Well, I'll talk first on a positive note. There's a lot of unknown, and I'll get to that. But on a positive note, the advances in genetics, starting with the human genome in the early mid to late 90s, advances in human genetics have really been incredibly advancing for medicine, for our understanding of disease, designing treatments for disease. I mean, really now we're in an age where we can have quite precise therapies and really effective therapies and specific diagnoses, right? Not catch-all diagnoses. So an example of that, a really great example of that, is in cancer therapy. I mean, 10, 20 years ago, cancer was really a disease where patients had radiological therapy, they had surgeries, they were really kind of go and get the tumor or try to kill it with either a chemical poison or a radiological poison and hope you don't kill good tissue and bad. And now, with an understanding at a genetic level of cancers, there are many cancers now where we have precision medicines or cell-based medicines that are much, much more effective. Jimmy Carter, president who died recently, he would have died 20 years ago without these advances in therapy, as an example. So coming back to your, what don't we know and what are the challenges? Well, in the nervous system, in the brain, all this is harder because, it's inside your head. You have a barrier from the blood. So getting drugs into the brain is harder. Obviously, if there were a tumor, like a glioblastoma, a terrible tumor, and that's in your brain, it's much harder than if the tumor is in your liver, where you can do a biopsy, or on your skin, where you could do a biopsy in an outpatient office. And that biopsy could tell you about the genes that would then allow you to pick medicines off a shelf in the best case. In the brain, much harder, right? So these are big challenges, but I do think, things that we learn about biology elsewhere in the body can also really lead the way in the brain. And oncology is a good example. I mean, I think glioblastoma treatment will certainly benefit from, for example, oncology of solid tumors in the body.
There's a couple FDA approved treatments for ALS, but I guess they're not treatments, but they slow down the progression of the disease. So if there's nothing that can reverse it, but there are some options that slow it down, what's being done for earlier detection of ALS?
Yeah, I mean, this is, I think, a very fair assessment. It's not what we have in terms of therapeutics is just the beginning, and they're clearly not good enough. And what I would say is that, this is a very active space, ALS drug development. Things that your audience might want to keep their eyes on. There are, as I mentioned, there are genetic forms of ALS. So there are, let's say, half a dozen to a dozen genes where mutations in these genes will cause ALS or are very likely to cause ALS. And these genes several of them are being very actively explored as targets for therapies. So one of the recently approved drugs is against a gene called SOD1, and this is a program that Biogen led, Biogen and Ionis, I think. And the SOD1 gene has a so-called gain of negative function. So the gene in people who get SOD1-related ALS, the gene it has a mutation that causes bad things unrelated to its normal function. And the therapy is simply to prevent that bad gene from being expressed as a protein. Okay, so it blocks the effect of that gene. And that therapy was approved by the FDA. And it's interesting, it was such a transformative therapy that it was approved even though the clinical benefit is probably not great yet in terms of outcomes. But the fact that they could show they could remove this gene, they could target it, and they could do what they needed to do molecularly was enough. And I mention that as a story because that shows you that the field is on the march. And for many of these genes, I think there will be some success in mitigating the terrible outcome of ALS. And it probably will, it'll take some time. And you see this with Alzheimer's disease as well. The first therapies, they didn't really work. They were controversial. Now it seems like they're starting to work. And so that, I expect that momentum to continue. It's a natural question to think, okay, if you develop a therapy for a genetic subset of ALS patients, is it only going to work for those patients? And those are things we have to learn. I mean, you could argue this both ways. It might be that some of these targets will be effective for a larger fraction of the patient populations, not just those who have the bad genetic form, but that has to be established. So I think there's real cause for hope. And there's a lot of really specific and I think very precise, incisive paths that are being explored.
You mentioned obviously there's a genetic component, but also a variety of other factors that are somewhat unknown, maybe some are known. Are you familiar with a study from a few years ago that looked at the association between like NFL players and ALS diagnoses? Yeah, so saying something along the lines of people are 4 times more likely to develop ALS if they played football. And I think there was also a correlation between the length of career and the severity of ALS. So is repeated head trauma one of those confounding variables? And if so, between the research that's been produced on CTE and stuff like ALS, do you think the public is taking that seriously enough?
No, I mean, I think it's been, I think anyone would have to say that this has been shocking and that the alarm, if anything, the alarm has mounted. I mean, I'm a sports fan. I like to watch the NFLs, but I will say that it is extremely alarming that, and it's extremely clear that repeated and strong force, applied to the head, like you have, and certainly in pro football and in boxing and some other sports, we have to really think about what we can do to limit that, because it is very dangerous. There's a lot of overlap, interestingly, between these kinds of chronic traumatic encephalopathy mechanisms and what we would call, there are diseases that, neurodegenerative diseases that are often called misfolded protein diseases. These diseases include ALS, Parkinson's disease, Alzheimer's disease, and in chronic traumatic epilepsy, chronic traumatic encephalopathy, you see similar neuropathology to some of these other diseases. So the neurons they look in histopathology like some of these other diseases. And we don't understand exactly why, but probably at the cellular and molecular level, there are similar things happening.
Are you collaborating then with people who are researching Parkinson's, people who are researching Alzheimer's? Is there overlap in your research?
There's definitely overlap in Parkinson's disease. And I have many close colleagues, and I pay fairly close attention to the Alzheimer's disease literature, particularly. And you could probably sense this. I personally particularly think that genetic clues in terms of genes that are implicated strongly in rare forms of these diseases. And I was just going to make the point that the human genetics, even in rare and small subsets of Parkinson's disease, ALS, Alzheimer's disease, that these rare genetics are really important for drilling down into a mechanism and identifying possible therapeutics. I think this is a really exciting area of modern medicine. And it's not just me that thinks this, because when for example, in some of these genes, researchers have discovered not only versions of the gene that will cause the disease, where if you have a genotype of someone when they're 30 years old, they're going to get the disease when they're 55 or 60 years old. Okay, so it's very powerful, very predictive in a classical genetic way. So that tells you the gene could contribute to a disease process. But in many cases, there are also versions of those same genes that protect individuals against the disease. So if you look population-wise, there are other mutations in the same gene, and people will, on a population-wide level, they'll be protected against a disease, even a kind of non-genetic form of the disease, right? So those two things together tell you that gene deserves attention, right? And maybe a therapy to make, for example, to make the bad version of the gene, the sequence of that protein, into something like the good version, right? That's a natural, logical thing to do.
We've talked about post-polio syndrome and MS on the podcast as well. My father was diagnosed with MS when I was in kindergarten, and through Therapeutics has the progression of his condition hasn't worsened drastically or as drastically as some other individuals I know with MS. But given the complexity of these like neurodegenerative diseases, how much interdisciplinary work is done, and maybe what breakthroughs are you most interested in or kind of looking at?
Yeah, I think in MS is a disease, as you I'm sure you know, that is really a disease of the nervous system. So nerves are attacked, but they're attacked by the immune system. So it's both a neurology and an immunology disease. And it's an autoimmune disease, right? So the immune system antibodies are attacking the peripheral nerves, these cells that are glial cells that myelinate nerves, and they're also centrally damaging nerves. I think it's good to hear that the therapy, at least some of the therapies for your dad have worked. They tend to be right now pretty broad. I mean, essentially, most of them you could classify as immunosuppressant therapies, and those come with liabilities because you need your immune system. So immunosuppression is not, can be dangerous and needs to be managed. When I was at Roche, they developed a drug called Ocrevus, which was an antibody that actually helped reduce B cells, and that seems to be a very effective drug. I think it's one of the leading drugs now for MS. But the real, I think the real challenge in MS now is there are therapies that can halt or slow the disease in many patients. It depends on the stage at which they begin their treatment. If the MS is too advanced, it can be much less effective, these therapies. So they talk about a relapsing remitting phase where the MS symptoms, come and go. And then there's a phase where the MS symptoms are kind of persistent and you don't get, near perfectly better. And I think we need therapies, obviously, to allow the nervous system and these myelinating cells to repair themselves so that those who suffer from MS and are at a plateau, they can come back and regain function. And there are a lot of companies working on this, but
yeah, I know some of our clients with MS at the gym have tried the same medication that my dad has taken, and it hasn't been effective for them. So it seems like it's a very individualized thing. But maybe on the topic of like pharma, do you think the last few years has made just like disseminating information and selling treatments, has it made it harder with the whole landscape of COVID and maybe some distrust that people have? Just is the prevalence of these messages making it harder to develop drugs and disseminate material?
Yeah, I mean, and I think it's reflective of the larger world. We're in a really fractured informational environment. It's easy for people to race ahead and to go and find what they consider to be relevant information. But it's a complicated world. If I said to you, okay, you're going to take a trip somewhere and you're going to go by airplane, you wouldn't think, well, I'm going to go to the internet and learn how to fly a plane and just see if I can do it. And I would just say to people it's great for people to go to the internet and sort of say, all right, I'm going to explore this topic. I can make decisions on my own. But I would make the analogy to flying that plane that, there's a reason why experts and institutions and so on, why we rely on them. And it's a really good reason. And it's the same reason why you rely on someone who's trained as a pilot to fly the plane. And you don't sit in the front seat and try it yourself, even if you might think I can do it, right? But coming back to pharma, look, pharma and biotech, it's a wonderful thing, but it's a system that is capitalistic. It's expensive to develop drugs. They are too expensive. There's no question about that. That the fact that they're too expensive means that there's problems with access. There are heartbreaking decisions, and different countries deal with this in different ways. The U.S. simply pays the highest bill, by the way. I could say as an American living in London. In London, they have a whole system where they consider which drugs are value for money, and they negotiate at a national level with pharma companies, and they get much lower prices for the same drugs. Sometimes they get them 6 months later, but if they're really important drugs, they get them. So, these are I'll tell you what the CEO of Roche, when I was there, I'll tell you what he said. And I think, there are going to be differences of opinions, and perhaps some of your audience will groan when they hear me say this, but he would make the point that when there's a transformative drug, like Roche's new drug for MS, which was a real step forward. There are some drugs for really devastating childhood diseases that have been, close to what you might call cures. Oncology drugs, there are drugs in this class. Once these drugs run their patent life, they are then, in a way, there's a legacy left for humanity. Okay, and there are drugs that were developed in, before the turn of the century that are still really important drugs. There are drugs, for example, immunosuppressant drugs, neurosteroids, etc., antibacterial drugs, epilepsy drugs, and those drugs have a high price. And then when they go off patent, there are many companies that can make them, and then we have them forever. Okay, so that doesn't free us from the ethical and moral quandary of, well, look, if my drug is $200,000 a year, do I lose my house to be well and to avoid death? That's a big problem. But it is, in the long run, I think, it is a system that has a happier ending than we sometimes think.
Yeah, it just takes long to develop. ALS and ataxia are conditions that not everyone may be familiar with. ALS is more public facing for sure. What role do you think the public awareness that's been generated from athletes like Pete Freights and Steve Gleason kind of has done for research? Does it trickle down to you? Does it just benefit the patients, although your work benefits the patients? But I guess what role does public advocacy and awareness play in studying a rare disease or a condition like ALS?
I mean, I think it's pivotal. Patient groups can really be involved, not only having a front row seat to the development of medicines, but speaking both to scientists and to pharma and biotech companies. And we see this, I see this very much with the company that I work with now in the rare disease space, where patient groups are absolutely essential, and their voice is a really important part of the hopefully the march towards a therapy. Also, regulatory agencies, the Food and Drug Administration, the FDA, definitely listens to patient groups. So there's political pressure, there's guidance that can be given to regulators about what aspects of diseases are most burdensome or where there's the most need for therapies. And I think on the general patient awareness front, I'll just give an example. We're doing some work on Parkinson's disease, and Michael J. Fox's foundation is really a pillar of Parkinson's therapy development and research. They've given out billions of dollars in grant funds. They really drive the field, and they do it not only at the early kind of research stage, preclinical research stage, but also with promising companies to make sure that it's a really vibrant ecosystem. So, so I would say to those inclined, you can really make an impact, and it's not just the money, it's the voice. Yeah.
Absolutely. Yeah, I like that. Is the work that you do patient facing at all, or predominantly academic and research based?
It's kind of somewhere in between. So I, with this company, we are developing and hope that within and it's the website, if you want to go and look, the website is lareotx.com. The company is, we hope, a year and a half or so, about 6 months from declaring what we call a clinical candidate, and then about a year from possibly going into clinical trials. So we're kind of, we're advanced in some senses, but still, there's lots of work to do. And in that role, I go to scientific meetings and I meet with patient advocates. I meet with parents at these meetings. So I go at conferences. You see and hear from people who are affected by the disease. In this case, the disease is so debilitating that the patients themselves are have profound intellectual disabilities. So it's a little harder to interact with the patients, but I certainly hear about them and about their lives and what is important to them.
What have you learned about communicating with individuals who have terminal illness?
I mean, I think one needs to listen. So I try. It's hard for me, but I try to keep my tongue tied, because every moment. I mean, if one doesn't have a disease oneself or in a close family member, you just don't know. You don't know where where all of the challenges are and where some of the joy is, if there is any joy. And I think it's so important to hear that firsthand, because not only, as scientists, we think I have a theory of what causes the disease or what might mitigate the disease, but hearing what really matters to people, what their challenges are, what they miss, what they'd like if they had only a partial therapy, what would it do for them? That's really important, because it can orient you to think about those things.
Yeah, the field of medical humanities is really interesting to me, and just the research on how outcomes can be improved by the way you communicate and the way that medical professionals communicate with their patients is a really interesting idea to study for sure.
Absolutely.
But it kind of goes like in the course that we teach to fitness professionals, we talk about the social model versus the medical model of disability. And obviously the medical model is essential for the work that you do. Everything is grounded in medicine, but there's also that social piece where sometimes a disability is just the product of either people not understanding or inaccessible societies. So it's cool to kind of have both things at play, and having medical professionals that understand that the therapeutics and the medicine is essential, but that there is that patient advocacy and understanding what they want to get out of therapy that is important. Yeah. I like the intersection of those two.
And there's no question that therapy, I mean, so many therapies, and this is particularly true of neurological disorders, having the right neurorehabilitation or having the right, tandem psychiatric treatment, along with, for example, a pharmacological approach, those two in conjunction are much more powerful. Indeed, some drugs just won't work without having the second component. So that's a key, and there are whole areas of research, as I'm sure you know, about how do you have the right rehabilitation component,
Absolutely. Maybe on the topic of SCA, could you explain to the audience kind of what ataxia is and how it's being treated and how it kind of manifests on a day-to-day basis for individuals?
Yeah, so ataxias and SCAs would be genetic forms of ataxia. There are other ways that ataxia can result. And in fact, there's one that probably many people have the most direct experience with, which is that alcohol causes ataxia. So the ataxia is just a medical term that means uncoordinated movement. And it can be maybe most apparent in someone's gait, the way that they walk, but it can also be apparent from the smoothness and the coordination of their movements. So in a neurological exam, a neurologist might ask someone to walk down a hallway and back, and a patient that suffers from ataxia might have a wider stance, and they might, have trouble with balance during walking. They might even need assistance with balance. So balance is a key part of this. Other features that a neurologist might look at are eye movements. So they might ask, put their finger up and ask you to follow their finger with your eyes. And they're looking to see, can you do that smoothly And particularly when you get to the edge of your gaze, is the gaze fixed, or do the eyes beat? You can't hold a gaze, and that's called nystagmus. That's a classic ataxia sign. Alternating movements, the neurologist might ask, someone to do this repeatedly, or to touch their nose and the finger of the neurologist. And ataxia patients will pass point, and they might have a tremor when they're moving, so they might, not be able to hit their nose. So all of these things, and then I mentioned motor learning earlier. Any kind of coordinated movement, like in sport or in music, where someone through practice will learn to make more precise movements, that is degraded in a patient with ataxia.
We see ataxic CP as one classification of cerebral palsy as well, that we will sometimes observe in clients. But what is the current treatment for ataxias? Is it different between SEA and other forms? Is there a genetic component? Is there a nurture component?
Yeah, most ataxia, the spinocerebellar ataxias, and also the what would call idiopathic ataxias, so cerebral palsy, ataxia is a nervous system insult from early life. There are chemical permanent forms of ataxia. There are autoimmune forms of ataxia. In all of these cases, the treatment right now is unfortunately largely symptomatic. So neurologists can prescribe medicines to make these things better, to reduce tremor a bit, to reduce other symptoms of ataxia. But particularly in the area of the genetic ataxias, there are many, many programs now where the genes are being directly targeted, and they are gain of negative function. So they're, a gene that's doing something untoward. And so blocking this gene is technically fairly straightforward, I'd say now. And the only challenge is, can you develop a therapeutic that's safe? And obviously that's effective, that blocks the gene effectively, doesn't block it too much in some cases. And there are many clinical trials now proceeding. So I'm hopeful, I am very hopeful that a lot of this stuff will, within the next 5 years, we'll see some drugs approved, and hopefully they'll have really high effectiveness, not just a little bit.
Yeah. For individuals that might be interested in pursuing a career in researching like neurodegenerative diseases, what would you recommend, or what is your advice?
Well, and I'm not just saying this because I grew up there and you live near there, but you could go to Boston. Boston, there's some good places to study in Boston, certainly. So I think there are so many ways to make an impact. And those can be, of course, to study a research area like neuroscience, or to study medical aspects of neuroscience that might be neurology or psychiatry. Those would be traditional ways. But I think patient advocacy, patient care aspects, nursing, rehabilitative care, these are all areas where a huge impact could be made. And, so I think there's clearly plenty of work to do.
What brought you to London? What brought you to London if there's so many good opportunities here in Massachusetts?
Yeah. This is like what my relatives in Boston say. But it is a fair question. It was a meandering path. So I had a faculty position after I finished my PhD and did a little bit of extra study. I had a faculty position in Los Angeles. So I worked at UCLA for many years. And then, really jobs and challenging jobs that I thought would be good for me. drew me first to Switzerland, to Basel. So I went from academia and I went to work at this drug company, Roche, which was really thrilling. It was exciting to see how medicines get made at scale in a big company like that. And then I had an opportunity to come to London, which is back a bit more in academics, but also with the freedom to work to develop this company. And London's been great. I mean, it's nice to live in different places, I think.
I can't relate to that as someone who rarely leaves Massachusetts.
Wonderful.
Not sure I've left Lancaster in a couple of years, but no, that's awesome. A lot of our audience is in the health and fitness space. Do you see any overlap in terms of what you do and maybe what someone can do to improve, I guess, their health and fitness, and just in terms of like recreation?
Yeah, well, I mean, it is an established fact, and I'm sure, most of your audience probably knows this and feels this, that physical fitness throughout life is the single most important thing you can do to stave off disease. And that's true of neurological disease. And it's certainly true of cardiovascular disease, other big areas, and metabolic diseases. But in the neurological space area, in terms of dementia, age-related dementia, if someone's active, it's a major factor in the plus column in terms of staving off cognitive decline. So absolutely keeping fit. And then there's the mental aspect of it. For most people who are physically fit, I don't know if I'm physically fit, but I would certainly say about myself that physical activity and even being, walking around, being whatever your choice of physical activity is, but it can be more strenuous or less strenuous. It bears mental dividends, mental health dividends, where you're clearer, you're able to deal with stress in a better way. And those things obviously also are really crucial for health.
With ALS being a decline of physical function, are you familiar with anything that correlates activity levels and the progression of the disease? Not to imply that you can reverse it in any way just by being more active after the diagnosis, but has that been shown to prolong it? Or I was even like, I didn't have a thorough conversation about it, but I remember talking to a muscular dystrophy researcher a couple of years back, and he said in some cases they advise against exercise because it almost expedites the decline of motor ability. So are you familiar with any research kind of correlating physical activity and the progression of the disease?
I mean, I'm not an expert in that area of ALS field, and muscular dystrophy is a very specific disease. So I think there's probably specific aspects. I think in general, within reason, and both for mental and physical benefits, having some activity that is where there's in the case of a severe disease, there's guidance from a rehabilitative therapy specialist. This is a positive thing in most circumstances. And but of course, for very severe and rapidly progressing, they use the word progressing for these diseases, which always sounds wrongheaded to me. But anyway, they call it rapidly progressing diseases. They're not going to be, they're not necessarily going to slow the disease. And that, and I think that also, that's one of the many tragedies of the disease, in that many of these neurodegenerative diseases and diseases of later life, the loss of mobility is really a very negative aspect of the disease, and it can make it so that it's harder to stay healthy in other aspects. That's
Yeah, the loss of independence is, I would imagine, incredibly frustrating. What are you most excited to work on over the next maybe 3 or 5 years?
well, the current project on genetic pediatric epilepsies is really invigorating. So I'm hoping that we can make real progress and bring something into the clinic that has the potential to be a medicine. And it's, I think our ideas, they're pretty bold. So I'm excited about that. Um, I'm excited as a kind of bystander, a well-educated bystander, to see some of these other programs in ALS and spinocerebellar ataxia, Alzheimer's disease, these therapy developments for these truly terrible neurological diseases. They're advancing, and I'm really hopeful that we might have an inflection point where there's a new therapy and it's really clearly a winning drug. It would be so satisfying for science and for the patients and everything to see that.
Absolutely. Yeah, that's a good, hopeful kind of way to maybe wrap up some of this and in a topic that is incredibly challenging and can be disheartening, I would imagine, working with patients that have to deal with these conditions. Hopefully, there are a lot of progress that's made over the next few years in how we treat them. So, Tom, thank you for sharing your expertise and doing my best to keep up with the topics that you were covering. But if anyone is interested in kind of learning more about the work that you do, is there a specific place that they can find you or resources that you would direct them to?
Yeah, I mean, my home is, as you said, at the University College in London, and so you can find me. You can find me on the web. My email address is totis@ucl.uc.a. I'm sorry, .ac.uk, academic.uk. And yeah, I mean, who knows? Maybe we'll see each other at a conference or some other event, or in Massachusetts.
Absolutely. Next time you come back up to Mass, if you've been visit Dennis or anyone, you'll have to stop by the gym and see what he's working on with us. But we can put that stuff in the show notes, your email, and then the companies you're working with. So, Tom, thanks again. I really enjoyed a conversation and hope that the audience finds value in it as well.
Thanks so much. It was really a pleasure from my end as well.
Thank you for listening to the AdaptX podcast. Our effort to amplify the ideas of our guests and create more inclusive and accessible industries is futile unless these episodes reach a larger audience. If you enjoyed our discussion today, please leave us a rating or a review on whichever platform you use. And if you would like to learn more about AdaptX, the course that we teach to health and fitness professionals and the projects that our organization is working on, you can subscribe to our newsletter through our website, www.adaptx.org. Until next Monday.